So next topic is ConstexpR. So in the past, I was doing this after the template meta programming section, which we don't have anymore. But the idea is that in the past, you could have done computation at compile time by using template tricks. So for instance, if I want to sum the first n integers, I can create a class sum and the integer I, and I could do something like this, static const long int, and then value I, so I take the value of the template plus sum of I minus 1 column value. So I instantiate the same class with the lower value, and then I have a specialization for where the sum, where the integer is 1. In this case, I return 1. So what happens here is that when I instantiate sum 16 column value, I go to 16 plus sum 15. The sum 15 goes to 15 plus sum 14, and then until you go to 1, you unroll it, you get all this thing, and at compile time, you will get the sum from 1 to 16, which is 16 times 16 divided by 2, whatever number it is. And this is what you would have done before the ConstexpR, or before. In this case, ConstexpR, also C++11, could have done much better work. And this is a template mechanism. It's complicated. There are people that really hates it, and debugging is very difficult. So what else? What can we do? So in the regular way, you will write something like this at runtime. You write a recursive function. So if the ID is greater than 1, then is ID plus ID minus 1, sum of the ID minus 1. If it is equal to 1, it is just ID. You sum the value at runtime, you get your recursive function going. This is compiled very quickly, and the code is compact. You can debug it, etc. So now with ConstexpR, you can just put ConstexpR in front of your function. It's not the case that I wrote it with this syntax here instead of an if. I didn't put an if because in C++11 it would have been complicated. But this is now you could write more general ConstexpR. So I will come to it. So the compilation is also quicker. You don't have to instantiate templates. And you can call this function sum at runtime. So you could do SDC out runtime, sum runtime, and whatever value is there. But you can also do static assert. So you can check at compile time that sum 16 is whatever greater than 0. Or maybe you want to check that it is exactly the value that it is. And so this sum 16 is actually compiled, is actually evaluated at compile time. So this function is executed at compile time, and the result is given to you. So this is what the ConstexpR can do for you. You have a note to self from a version of me from the past, yeah?
Is it like a modifier that I can have, let's say, the same signature, the same function, but one is ConstexpR? No. So all the
ConstexpR is not part of the type system.
Okay.
So you cannot have. So you, as we will see, we can have a ConstexpR variables, but it's not. ConstexpR is not part of the type system. Note to self, yeah. Wait, there's a microphone behind.
What are the limits of this compile time evaluation of functions?
There are limits. It depends on the compiler. So for instance, this recursive thing is usually a compiler option. For instance, I think there was a problem in the GCC. I mean, I think, yeah, it was GCC where recursive templates went up to 900 steps and ConstexpR to 512, for instance. But then you have an option to say more. You can make the number bigger, but there are limits. And the limits are due to the implementation.
But in practice, could it do some longer calculation?
You can do a lot of stuff. I've seen people doing, there was no, that was done with template meta programming. Someone implemented a video game in template meta code where you basically have to compile, generate code, recompile, make your own move, compile and see what the output happened. You make another move, compile it again. There are like compiler, language compile. There is a programming language which is called brainfuck, where it's the real name, where all the program is specified by using weird symbols. So you can program anything you want, but it's all about the slash greater than whatever. So someone implemented a compile time brainfuck interpreter. Now, you can do as crazy thing as you want, basically. The template metaprogramming and ConstexpR computing are completely Turing complete. You could do whatever you want. But of course, you have some limits, and you shouldn't really push it beyond what is reasonable. But in principle, you can increase. For instance, if the recursion thing gets out of stack, basically you have too many calls to recursive functions. There are options in the compiler to increase the amount of storage that the compiler can use for doing that. But if you're really exploiting that thing at that level, probably you have to rethink your code, I would say. So there are things for which these things are very useful. Others is just to experiment and play and have fun, but maybe not for production code. So, yeah.
What did you mean by the ConstantExper is not part of the type system? You said that, right?
So you cannot have a function behave differently if you're passing a ConstexpR variable. You cannot do overload resolution based on the fact that something is ConstexpR or not. That's what it means. This is why it's not part of a type system. So let's see. I don't remember this node to self, like the good node selves. This is why it's there. Let's see what it does. Oh, come on. All right, this if I do 0, let's see what happens. So this is the code that does the ConstexpR sum of the integers. And can everybody see the screen? Yeah. So here I have the sum of int function being compiled, right? It's here. Sum of int, this is the compile time, so it's not the ConstexpR, it's actually the runtime version compiled, which is this one. I go here in main, and I see I have 16. I put the 16 inside this argument, inside this register, and then I call sum of int, and then I will take the result, and I print it. right? So this is the runtime component. And there got to be somewhere, again, maybe another call. It might be this one. Is it? No, it cannot be that one. What is it? 16 times 17 divided by 2. Or 17 times 8. So it's not this one. No, 17 times 8. Yeah, 136. I know this, I think it's here. This is, I think it's here. I don't know. Let me, do you see where the second one? Okay, we can go here.
Static assert.
Static assert.
Doesn't affect
Yeah.
the code generation.
Yeah, sure. Absolutely. Yeah, I don't know why I was looking for it. Yeah, it's just, note to self. Don't search for static assert in codes. Yeah. And then you can turn the optimizations on, and then you will see actually the compiler here did the computation itself. But not because it's ConstExper, right? It's just because it could do it. It is ConstExper. It is a constant value. And, well, these can be compiled at compile time, right? This is ConstExper. In some sense, saying this is valid. You can do it at compile time. And here you see 136, and you print it.
And what if we remove Constexpr and static expr?
Oh, yeah. Let's try. Good question. Oh, some int. So even with optimizations, the function is there. And it's actually pretty long. What the? Nice. But then still. All right. Yeah, the function is compiled. It is available in the binary, but that particular value is being.
You can do it in line.
Yeah, in this case, the function is not there. Yeah. Yeah. No, it is. Well, it is in the inline is available in the translation unit. So it will not be available in other translation unit. While if you put it non-inline, it has to be available. I think for ABI concerns. Note to self. No more note to self. All right. Hello? Okay. Okay, so the ConstexpR indicate that expressions will be evaluated and available at compile time. As we see, a ConstexpR may or may not return a constant expression, as in this previous example here. This is you can have the runtime version of this function. But when I require that to be a constant expression, it will happen as a constant expression. It will be evaluated at compile time. So if I'm using the ConstexpR functions in the ConstexpR expression, then I will be guaranteed the thing happens at compile time, or I have a compile error. So I can define my ConstexpR float variable d, and I put it to 13.2. have a ConstexpR function that returns a double. And then I can simply do static assert, D is equal to this, and F is also equal to D. When I evaluate the function, it will be evaluated at compile time. The nice thing is that the standard allows you to use the ConstexpR functions also with const. So I have two functions here. It's SQR1 and SQR2. The first one is ConstexpR. It's making the square of the number that I pass in. And I have a class A, which is templated with a number. And now I want to instantiate my class with, so I have a const int x equal 2. And then I do A of SQR1x, and I instantiate my list 1 with that. And that actually works. So this SQR1x is evaluated at compile time, will return 4, and I will instantiate A with 4. But the second one will not work, because I can call SQR2 with x, but not in this context here, because here I need the compile time value in order to instantiate the template. Yep.
And so far, you can't use the float for templates. You said yesterday, no? Or can you?
Yes. Yeah.
So you can't use that for like doing square root of whatever float.
Yeah, for a float it wouldn't work. No. C++20, if that passes, you can do it. But yeah, I don't know. The idea is that if you can do computation at compile time, it saves you the trouble of figuring out at runtime, or using virtual functions, to use inheritance and all runtime tricks. If you can do stuff at compile time to just get the computation you want, then you save time. You spend the time in compilation, but not in the not at runtime. And of course, SQR1 can be used at runtime too, and while SQR2 can only be used at runtime. You can also use in initialization. So here I have a function foo that takes an integer and squares it, and a Sifu, which is the ConstexpR version that squares the number, same signature. Now I can do a static const int foo of 10. And this works. And also the second one works. I have ConstexpR int y is Sifu of 10. So a static variable is initialized before main, if you want. Take the simple way. So these variables are basically, this static const x is a global variable. It's available, and it is initialized before your program starts. And the ConstexpR version, you could do ConstexpR int y Sifu of 10. But I cannot call foo of 10 with the ConstexpR, because if I call foo of 10, this is just a runtime function. So this thing happens by having foo be called, this basically before main starts. You call foo, you initialize x. So then when you enter main, x is available, you can print it. but the ConstExper int is available only as a constant expression, so you can only initialize with ConstExper. And I see I have a link on the Godbolt too. Interesting though is that this static constant can also call Sifu, because Sifu is available, can be used at compile time and also at runtime. And let's see. What we have here. No, it's a fusi instead. That's a Sifu. And now I have, I'm printing, I have something initializing x with 100. You see, this is actually the sub foo int, so it's kind of a subroutine foo that initializes x, but I have the constant expression here. So the constant expression is the y, and you see there's no line here. There's no compilation line here. You see there's no color in this line. This one is just printing 100, and this one is printing x. But x is going to be initialized here, which is called before main starts. So what are the constraints, though, for using ConstExper? Many constraints has been removed in C++ 14. So before C++ 14, there was ConstExper. There were a lot of limitations that limit really what you could do with this technology. But now you can have local variables. You can have if statement. You can have multiple return statements. So now in C++ 14, you can have a function returning auto, and you have multiple return statements inside that function. And the rule is that all those return statements must return the same type. But then you have an easy way to basically specify the return value. And you can also do it in the ConstExper functions, literal arguments. Yeah, basically you have to have something that is available at compile time, no static variables. You cannot have virtual ConstExper function. Virtual works only for runtime. And before C++ 17, you could not have lambdas that are ConstExper. In C++ 17, they introduced ConstExper lambdas. And you can have ConstExper variable, but it must be literal type. It must be initialized there. You cannot define a ConstExper variable and assign a value later on. No, it must happen where the ConstExper definition is. And of course, the old expression has to be ConstExper. It has to be evaluated at compile time with the ConstExper rules. And as we were saying, ConstExper is not the type traits. It's not a qualifier. It's not part of the type system. You cannot customize a function based on the fact that something is a ConstExper or not. I think there is a proposal around to allow ConstExper function arguments, but I don't know if that will ever pass. The interesting point about ConstExper is that now we have seen ConstExper to compute integers, to compute float and double, but we can use ConstExper to construct our own objects at compile time. So we can have our objects, which can be created at compile time, used at compile time, and we can do computation at compile time with those objects. Again, C++ 11 is very limited in what you could do, but C++ 14, you basically you can construct an object at compile time by basically obeying the rules of ConstexpR functions, and so it's pretty powerful. There are some constraints still, so you cannot have virtual base classes. You cannot. The data members must be constructible at compile time. I mean, everything has to be available at compile time. And let's see an example, because listing rules doesn't help much. Do I have an example? Yeah. So in C++14, you could do a full function. So this is basically a full ConstexpR function. You take a function F3 that takes a tuple. A tuple can also be constructed at compile time if the types are constructible as constant expression. And then you can say, you can make a tuple 1, 2, 3, 4, and you can construct this tuple at compile time. And you can have runtime conditions if the condition is true, which is if the third element of the tuple is less than the second element of the tuple T, then I return the second one, otherwise return the first. And this can be done at compile time, also with multiple return statement. Yep.
And in the generated code, you'll have only the condition that is true?
In the generated code, you don't see anything. If this, okay, in this example, actually, I've noticed that I'm actually doing it at a runtime. But if I'm doing it at compile time, there is nothing in the object file. You don't see any function. There's no, this is not an if statement that is evaluated at compile time and only the right branch is happening. This is just a function. If I'm doing this in the right way, so at compile time using ConstexpR here, this will be really code computed by the compiler. Basically, the compiler interprets the code and gives me the result out. I don't see anything in my object file. I might see the function, actually, but it might not be called. In this example, it is runtime, yeah. This is a wrong example. I wanted just to show that you could do this, but then I didn't pay attention to the main. And I can also use it to construct my objects. So now I have my class, which I call const_a. It has an integer member function, m_i. This doesn't have to be ConstexpR, actually. It has to be just an integer member. And I have a ConstexpR constructor. And here I'm basically inflating with all the things you could put in there. Wow. I will try again. So here, basically putting this conflated stuff, it can be template, it can have condition, you can have multiple statement. You just put in there all the stuff you could put, but not because it's anything useful. And the only thing that is useful here is this one. If I am initializing the data members in my ConstexpR constructor, it must happen as an initialization list. So after the function column, initializing my data member. That's the only constraint, I think. But then I have a ConstexpR constructor that takes a T and tuple, that is a tuple, and access the members, and that's exactly as it did before. And I have a member get that returns my member and is also ConstexpR, and now I can do ConstexpR auto, I can create my tuple at compile time, and I have, well, this should be const_a. So ConstexpR, my const A class, I constructed with this tuple. Writing ConstextExper here is actually essential, right? Because I'm telling this is code that has to be evaluated at compile time. And then I can check that my struct.get is equal to 2 at compile time. And if I write this code, nothing is actually produced in the output, kind of. It's like just evaluate. This is all computed at compile time by the compiler. So basically, the only restriction is that data members have to be initialized in there. The standard well, it's not the STL. It's the standard library. It has several functionalities that are ConstexpR, and some that are not. So std pair, tuple, array, and also bitset can be constructed at compile time. And we have seen already std array. We have seen tuple. Std pair is basically a tuple of 2 elements with a very ugly interface. And all the other, this one are not. So you cannot construct std vector at compile time, or std string, or std function. So there's still things you cannot construct at compile time. In C++ 14, you can have initialized list, which are ConstexpR. So you can have an initialized list constructor, which is ConstexpR. And the lambdas are available only in C++ 17. And what you can do is basically define a function, a lambda, a ConstexpR lambda, which return 5. And of course, the rule has to be that it has to be evaluated at compile time. So in both cases, the static assert f equal 5, and f underscore equal 5, f equal 5 are equivalent. So this, you could do it before C++ 11, right? You can have your function, ConstexpR function. And this is another example in which you can see that if you use lambdas, you can keep your code at your site. Before, this function had to be defined somewhere. Now you can define your stuff in where you're actually using. Yep. Can you pass the microphone to you?
So you don't need to specify returnint on the first line?
No, it will be deduced because it's auto. So the return will be integer because I'm returning an integer. But this is not ConstexpR. This is just C++ 11 or 14.
So why do you need it in the second one then?
Here, I don't remember. I think you don't need it. I think I just got the example from somewhere. I don't think you need that.
You don't even need flags. If there are no arguments, you can skip.
You can skip the, yeah. So suppose I have this ConstexpR function, which is divide. It takes an integer and it is recursive in this case. I want to basically, if ID is greater than 0, then I divide ID by the results of dividing ID minus 1. Otherwise, I return ID. And I want to return divide 4. Which will turn out is 4 divided by divide 3, which then is divide 2, which then is divide And at some point there is a divide. Actually, there is not a divide 0. But, so this code will actually run, because we checked that D is not 0. But if you compile this, you get a compilation error saying non-constant condition for static assertion. You cannot do compile time work for this. The reason is this division might triggers. If ID is 1, then this will become 0. You go here and become 0, then you turn 0, it becomes divide by 0. So it actually triggers the thing. So you get a compile error because this guy throws an exception, is a divide by 0 exception. And ConstexpR function cannot throw exceptions. So functions are not ConstexpR if they potentially throws or if the results is undefined. I tried this example, it doesn't work with this error. I tried last week.
You can explicitly throw.
You can explicitly throw, but not like this.
I don't think this is exception. It's divide by error is
Divide by 0.
divide by 0 triggers signal.
We can try later or tomorrow. But anyway, there are conditions in which the thing doesn't really make ConstexpR. I would like to do the integer sequence. Yeah, let's do that. Let's try. Suppose I have a function that takes a tuple and takes takes a tuple and takes a sequence of integers. And now I want to just get the values of the tuple corresponding to these IDs. What I can do is to use a pattern expansion where I do std get IDS, this is the parameter pack, tuple and dot dot dot, and this will expand to if the IDS is this, if this is an integer sequence and these IDs are 0, 1, 2, 3, 4, 5, this will become get 0, comma, get 1, comma, get 2. If the indices are permuted, you get whatever values you have in your IDS list. And this is a way in which you can access the this is a way in which you can convert the tuple into a pack, for instance, into a variadic pack again. It's not really a ConstexpR example. So if we want to I want to have a function that prints tuples, and I can do it by the usual tricks. So I can have the first argument and the rest of the arguments. I take the first one and I print it, and then I call print with the rest of the pack. And then at the end, if I have only one, I just do cout. So if I want to print the tuple, let's say I have this function here, right? This is the function that we saw earlier, and it just works, right? We can't have this function. But then we want to use it to print the values in a tuple. So I want to have a function which is print tuple, but how can I use that function to print tuple? Well, I can take my print tuple that takes a tuple. The tuple takes certain types, VSs, and the tuple is X. Now I can unpack my tuple, basically making the tuple into a variadic pack, unpack X with this make integer sequence size of size integer of size of. This will create something which is an integer sequence, which is this type here, integer sequence, with the IDs expanded to 1, 2, 3, 4 up to the size of VS. So now this make integer sequence is actually a ConstexpR function. It generates this type at compile time, and it passes to this to the unpack function where I pass my tuple, and then I call my previous print with the get IDs of the tuple, and I expand it. So now I can access all the elements of my tuples in a single call, and I can call my old function that prints the values. And this expands as get 0 of tuple, comma, get 1 of tuple, comma, get 2 of tuple, up to all the values. And this is the pattern expansion that we've seen. I have other examples, but it is an example of automatic differentiation. You can find it in the example folders, in which you have expression. You can write expressions, and you can automatically, at compile time, differentiate them and evaluate the derivatives of your expression. So you can have a compile time. You have one expression, which is x cubed plus the derivative of x squared, which was developed by one of our collaborators, and it was one of the first examples actually that we tried with the ConstexpR. But I think that is enough. Yeah. Questions? If not, we see you tomorrow. Thanks.